Have you ever stopped to think about how gasoline is made to the exact same quality every single time? Or how our power grid stays perfectly stable even when millions of us flip on our lights all at once? Well, the answer is this kind of invisible genius called advanced process control. It's really the hidden intelligence that makes sure all the complex systems that run our modern world are consistent, efficient, and most importantly, safe. So let's pull back the curtain and see how it all works.
But first, let's start with a really basic question. Why is it so hard to keep things perfectly stable in the first place? I mean, whether we're talking about the temperature in your house or a massive chemical reactor, things are constantly getting pushed and pulled by outside forces. So how do we fight back against all that chaos?
Well, the simplest answer is something called a feedback loop. Just think about the thermostat in your home. It's doing a constant three-step dance. First, it measures the current temperature. Second, it compares it to the temperature you actually want. And third, it acts by turning the furnace or the AC on or off. It's this constant cycle of correction, and this simple idea, it is the absolute foundation of all process control.
All right, so in this explainer, we're going to see how engineers have built on that really simple idea. We'll kick things off with the basic control problem, then we'll look at some cool strategies for getting faster reactions, beating annoying time delays, and even juggling safety versus performance. And finally, we'll peek into what happens when these controllers start getting seriously smart.
So let's dive right in with this simple control problem. And really, it all boils down to one thing. Just reacting to a problem after it's already happened, well, that's not always good enough.
Let's go right back to our trusty thermostat. If somebody throws open a window on a freezing winter day, a simple controller only knows the room is cold after that blast of cold air has already hit the sensor and the room temperature has started to drop. It's always playing catch-up. Now, in an industrial plant, that kind of delay could ruin a multi-million-dollar batch of product, so not ideal.
This brings us to our first enhanced strategy, and it's a really cool one: cascade control. I love to call this the manager and assistant strategy, and you're about to see exactly why. Okay, so in a normal setup, the main controller, let's call it the manager, it tries to do everything by itself. It watches the room temperature, and it directly messes with the furnace valve. But with the cascade setup, the manager delegates. It still keeps its eye on the big prize, the room temperature, but it gives orders to an assistant. This assistant controller is laser-focused on something that moves really fast, like the fuel pressure going to the furnace. So if that fuel pressure suddenly drops, the assistant fixes it instantly, long before the room temperature even has a chance to change. The manager might never even know a problem was just solved.
Now, how you set this up is absolutely critical. You always tune the fast inner loop, the assistant, first. You get it running perfectly. Once that's stable and reliable, then you can tune the slower outer loop, the manager. The stability of the entire system really depends on getting that fast, dependable assistant right.
All right, let's tackle the next big headache: time delays. In so many industrial processes, there's a huge, frustrating lag between when you make a change and when you actually see the result. To solve this one, we basically need a crystal ball.
The problem is, you're essentially trying to control the past. I mean, think about adjusting the temperature in your shower. You turn the knob, right? But then you have to wait and wait for that hot water to travel all the way through the pipes. By the time it finally hits you, you've probably already overcorrected and now it's way too hot. This is a massive issue in places like chemical plants, where stuff has to travel down these super long pipes.
And here's what that looks like in action. At time zero, the controller does something. It opens the valve. Then, there's this frustrating delay where nothing seems to be happening. Finally, maybe 2 minutes later, the result shows up. A simple controller gets totally confused by this. It'll overshoot, then it'll undershoot, creating these wild, unstable swings in the system.
The solution, and get this, it was developed all the way back in 1957, is called the Smith predictor. It is an incredibly clever idea. Basically, it runs a digital twin, a super fast computer simulation of the process. So instead of waiting around for the real result, the controller gets an instant prediction from this model of what will happen. It gets to control the future, not the past, which effectively just erases that time delay from all its calculations.
Okay, so we've made our controllers faster and we've made them smarter about time. But, real-world systems aren't just slow, they are also really complex. What happens when a controller has to manage multiple goals that sometimes even conflict with each other? This is where they have to learn how to juggle safety and performance.
I mean, this is a classic problem, right? A chemical reactor needs to stay at a really high temperature to be efficient. But if the pressure inside gets too high, it could be incredibly dangerous. So what does the control system do? Which goal does it prioritize?
This is where we get into a whole family of smart safety net controls. Selector control, for instance, might look at 5 temperature sensors inside that reactor and decide to always react to whichever one is the hottest, just to be safe. Override control is kind of like a safety pilot. It's a secondary controller that just sits there doing nothing until a variable like pressure exceeds a critical limit. Then it jumps in and takes complete control to bring the system back to safety.
And then you have something like split range control, which is just a really elegant way to manage 2 opposing actions with a single signal. Take a look at this climate control system. One controller output can manage both the heater and the air conditioner. As you can see, the lower half of the signal controls the heater, the upper half controls the AC, and there's this nice little deadband right in the middle where they're both off. It's a seamless way to use multiple tools to get really precise control over one single thing.
And all of this leads us to our final section, the real frontier of process control. This is where these systems start to show off some truly intelligent, almost human-like behavior.
Because the real world is messy, right? It's not always a straight, predictable line. That's where nonlinear control comes in. For systems that actually change over time, like a filter slowly getting clogged up, we have adaptive control, which automatically retunes itself to stay at peak performance. But maybe the most interesting of all is fuzzy logic. This actually lets engineers program a controller using qualitative, human-like rules instead of just hard numbers.
And this quote just nails it. The key here is the heuristic approach. It's a practical rule-of-thumb method. So, instead of just relying on complicated math, a fuzzy logic controller can be programmed with concepts like a little too hot or slightly too high. It lets the system make nuanced decisions, a lot like an experienced human operator would.
And that leaves us with a final thought. All of these strategies, every single one, from the simplest feedback loops to controllers that can predict the future, prioritize safety, and even reason with ambiguity, they're all steps toward more and more autonomy. We are building intelligence right into the machines that run our world. So the big question for the future is, as these systems get smarter, how do we make sure we're teaching them the right rules and the right priorities to make the best choices, especially when things inevitably go wrong?